HW12 Question 1 Part D. Here, once again, it's an oxidation reduction reaction, and we're going to balance this using the half reactions method. Let's assign oxidation states to the low-hanging fruit, the easy ones. Manganese 2 ion is alone and it bears a charge. Whatever that charge is will also be its oxidation state. Bismuth 3 ion is alone and it carries a charge. Whatever that charge will also be its oxidation state. So plus 3 for bismuth. Now for the other species, we have sodium bismuthate. You see the sodium ion in there. Let's break this apart. We've got sodium ion, and we have whatever would be left after sodium ions broken off, BiO3. Here we see that sodium is alone and it bears a charge. Whatever that charge is will be its oxidation state. Within BiO3 minus, we have oxygen, which is the more electronegative atom. It'll take a -2 charge. Bismuth will take whatever charge it needs so that when the oxidation states are added together, it'll match the overall charge for that species, which is a -1. Let's do a little bit of math here. One atom of bismuth, whose oxidation state is unknown, when added together with 3 atoms of oxygen, whose oxidation state is known to be -2, should add up to the overall charge of -1. Adding 6 to both sides, we see that x becomes 5. So x in this case is a +5. The other species that we should tackle, a little bit tricky, is the permanganate ion, MnO4 with a 1- charge. That's one of your polyatomic ions. Of course, oxygen is more electronegative than manganese. So we'll solve for manganese's oxidation state. 1 atom of manganese, when added together with the 4 atoms of oxygen, whose oxidation state is known to be -2, because it's the more electronegative atom, should add up to the overall charge, which in this compound is also -1. A little bit of math helps us to arrive at the oxidation state for manganese. +7, what? That's a really high oxidation state. Manganese is a ridiculously good reducing agent. Or I should say oxidizing agent, because it wants to be reduced. So let's record those oxidation states. We had +1 for the sodium, +5 for bismuth, -2 for the oxygen, +7, ridiculous, for the manganese, and then a -2 for the oxygen. What got oxidized and what got reduced? Well, manganese started out at a +2 and it went up ridiculously high to a +7. It's oxidized big time. The other element that changed was bismuth. It's +5 on the left side and only +3 on the right side. So it was reduced. The other elements, sodium, is just a +1. We don't see sodium on the right side of the equation. That's going to be an interesting conundrum when we get to the reduction half reaction. I'll show you how to handle that in a second. And then oxygen doesn't change. It's a -2 on either side. Let's break this apart into half reactions and tackle it from there. So starting with the oxidation half reaction. We have manganese 2 ion on the left side of the equation and the permanganate ion on the right side of the equation. We'll apply our steps of redox balancing. Step 1, balance elements other than H and O. In this half reaction, we have 1 manganese atom on the left side and 1 on the right side. So that balances. Balance oxygen using water. we have 4 oxygens on the right side. That means that we need to add 4 water molecules on the left side to make the oxygens balance. But that threw off our count of hydrogens. Now we have 8 unaccounted for hydrogens. We better tack on 8 hydrogen ions to the opposite side. Lastly, we balance charge using electrons. Let's do a charge counting. 4 species which are neutral, plus 1 species which is double positive, gives us a +2 charge overall on the left side. And on the right side we have 1 species that's single negative, plus 8 species that's single positive. Wow. That's +7 overall. To make the charges match, we can only reduce the charge on the side that has a higher charge. You can only add electrons. So where we see a +7, we need to add 5 electrons. The difference between 2 and 7 is 5, which means we knock the charge down on the right side to a +2, and now the charges match on the left and right sides of the equation. Let's tackle the other one. In the reduction half reaction, we started with NaBiO3 on the left side and Bi3+ on the right side. Now here's where it gets really tricky. Step 1 of balancing half reactions is to balance elements other than H and O. So there's 1 atom of bismuth on either side, that's fine. But there's only an atom of sodium on the left side. Here's where we have the trouble. You're not used to doing this, but because sodium ions are part of the compound, sodium bismuthate, they are floating around in solution. So to make this equation balance, we have to add a sodium. And that's going to affect the charge, which will affect everything else in terms of balancing. So we had to add that sodium to make elements other than H and O balance. Next step, balance oxygen by adding water molecules. Well, we have 3 oxygens within NaBiO3, so we need to add 3 water molecules to the right side. But upon doing that, we've thrown the hydrogen count off, so now we need to add 6 hydrogens to the left side. Lastly, we balance charge by adding electrons. On the left side we have 6 species which are single positive in charge, and 1 species an implied 1 coefficient, with a neutral charge. Overall that's +6. On the right side, 1 species that's triple positive, plus another species that's single positive, plus 3 species that are neutral. So a triple positive and a single positive adds up to a +4. We can only bring charge down by adding electrons. So the side that has the higher charge will receive the electrons, and the number of electrons will be equal to the difference in charge between the 2 sides. In this case, the difference between 6 and 4 is 2, and that's why we added 2 electrons. Upon doing that, we knock the charge down on the left side to a +4, which makes the charges match on either side of the equation, and that's what we need to do. Okay, we've balanced the 2 half reactions. Now we get to figure out how to add the 2 half reactions together. Crucially, we need to make sure that the number of electrons gained in the reduction half reaction is equal to the number of electrons lost in the oxidation half reaction. Since those numbers 2 and 5 do not match, we have to multiply the entire equations by some coefficient so that the 2 and the 5 match. In other words, we're looking for the lowest common multiple between 2 and 5, and that would be 10. So we're going to take this entire oxidation half reaction equation and double all of the coefficients. We're going to take the entire reduction half reaction equation and quintuple the coefficients. Yikes, let's rewrite these. Notice the really high number of hydrogen ions, 30. Yikes. Now we can add the two half reactions together, and crucially the number of electrons cross out. 10 electrons lost in the oxidation half reaction matches the 10 electrons gained in the reduction half reaction. You can also look for other things to cross out. For instance, actually nothing else. Oh, yeah, yes we do. We do see. So I see 8 waters on the left side in the oxidation half reaction and 15 waters on the opposite side in the reduction half reaction. Since they're on opposite sides, they'll cancel out. So the 8 water molecules will cross out and will knock the number 15 down to 7, which is 15 minus 8. Then we can rewrite what's left, and we should have our final answer. And bada bing, bada boom, you have a nicely balanced oxidation-reduction reaction found using the half reactions method.